Good evening, and welcome back to Boring Science for Sleep. Tonight, we're going to take a slow and gentle journey far beyond the familiar skies of Earth into a universe filled with worlds we have never seen and moons that may circle them quietly in the darkness. But before we begin, take a moment to settle in. Dim the lights if you can. Find a comfortable position. Let the day slowly drift away. And if you'd like, leave a comment below telling us where you're watching from and what time it is there. It's always peaceful to see listeners from all over the world relaxing together beneath the same universe. Now, let's begin our quiet journey. On clear nights here on Earth, the moon rises gently above the horizon. Sometimes it appears as a thin silver crescent, sometimes as a glowing half circle, and sometimes as a full, brilliant disk lighting the entire night sky. For thousands of years, people have watched this familiar companion drifting silently across the heavens. The moon feels so natural to us that it's easy to forget something remarkable. Our planet is not the only world with a moon. In fact, moons are everywhere in our own solar system. Jupiter alone has more than 90. Saturn has dozens more. Some are icy worlds covered in frozen oceans. Some hide vast liquid seas beneath thick crusts of ice. And some are even larger than the planet Mercury. Moons, it seems, are a very common part of planetary systems. And this leads to a quiet but fascinating question. If moons are so common around the planets in our own solar system, could they also exist around planets orbiting other stars? Planets beyond our sun are known as exoplanets, and moons orbiting those distant worlds are called exomoons. Imagine standing on a distant planet somewhere in our galaxy. The sky above you is unfamiliar. The constellations are different. The star that warms your world glows in a different color, perhaps orange, perhaps red, and rising slowly over the horizon, another world appears. A moon. Maybe larger than the moon we see from Earth, maybe smaller. Perhaps it glows faintly blue from reflected starlight, or perhaps it is covered in clouds and oceans shining softly against the alien sky. On some planets, there might even be multiple moons, several distant worlds slowly drifting across the heavens night after night. A quiet cosmic dance. For astronomers, the idea of exomoons is incredibly exciting. If moons are common in our solar system, then the galaxy may contain billions of them. Some might be small rocky moons like ours. Others could be giant icy worlds like Europa or Titan. Some might even have oceans beneath their surfaces. And, in the most fascinating possibilities, a few exomoons might even possess the conditions needed for life. Entire worlds, orbiting not stars, but other planets. And yet, despite decades of searching, astronomers have not yet confirmed the discovery of a single exomoon. Not one. This may seem surprising. After all, scientists have discovered more than 5,000 exoplanets orbiting distant stars. Surely at least a few of those planets should have moons. But finding them is incredibly difficult. Moons are small. They are faint, and they orbit planets that are already extremely far away from Earth. From our perspective, the signals they produce are delicate and subtle tiny disturbances hidden within the light of distant stars. Detecting an exomoon is like trying to notice a firefly circling a lighthouse from thousands of kilometers away. And yet, astronomers continue searching, because the discovery of even a single confirmed exomoon would open an entirely new chapter in our understanding of the universe. It would reveal that moons are not only common in our solar system, but throughout the galaxy. It would suggest that distant planetary systems may look far more familiar than we once imagined. Worlds with moons rising in their skies, night landscapes illuminated by alien moonlight, quiet companions orbiting distant planets under unfamiliar stars. Tonight, We'll slowly explore this fascinating possibility together. We'll wander through 100 sleepy facts about exomoons. Along the way, we'll discover how moons form, how astronomers search for them, and why these hidden worlds may be far more common than we once believed. And as we travel through these gentle cosmic ideas, let your thoughts drift slowly like distant moons orbiting quiet planets in the darkness of space. So take a slow breath, relax your mind, and let's begin our journey among the moons of other worlds. Before astronomers began searching for moons around distant planets, they first looked much closer to home. Our own solar system is filled with them. In fact, moons are so common here that nearly every major planet possesses a collection of these quiet companions. Earth has one. Mars has 2 small moons. The giant planets Jupiter, Saturn, Uranus, and Neptune each host entire families of them. Together, these moons form a vast and diverse population of worlds quietly orbiting the planets of our Sunday. And when scientists began discovering planets around distant stars, one simple idea naturally followed. If moons are so common here, perhaps they are common everywhere. Our own moon is the first and most familiar example. It rises slowly above Earth's horizon and has accompanied humanity for as long as our species has existed. Its surface is covered in ancient craters, silent plains of volcanic rock, and mountain ranges formed billions of years ago. Unlike Earth, the moon has no atmosphere and no oceans. It is a quiet, frozen landscape that preserves the history of the early solar system. Yet even though our moon feels unique and special, it is only one member of a much larger family. Across the solar system, moons appear in astonishing variety. Consider Europa, one of Jupiter's most famous moons. From a distance, Europa appears as a smooth, white sphere wrapped in delicate reddish cracks. These cracks spread across its icy surface like long, wandering lines drawn on frozen glass. Beneath that frozen crust, scientists believe there may be a vast global ocean, a hidden sea of liquid water stretching beneath kilometers of ice. If that ocean truly exists, Europa may contain more water than all the oceans of Earth combined. And within that dark ocean, warmed by the gentle flexing of gravity from Jupiter, scientists sometimes wonder whether life might exist. Tiny organisms drifting silently in the darkness beneath the ice. Another remarkable moon is Titan, the largest moon of Saturn. Titan is so large that it is bigger than the planet Mercury. But what makes Titan truly unusual is its atmosphere. Unlike most moons, Titan is wrapped in a thick golden haze. Beneath those clouds lie lakes, rivers, and even rain. But these are not made of water. Instead, Titan's lakes are composed of liquid methane and ethane, strange hydrocarbons that remain liquid in the cold temperatures far from the Sunday. If you could stand on Titan's surface, you might see dark rivers winding across the landscape and orange skies stretching overhead. A world both alien and strangely familiar. Then there is Ganymede, the largest moon in the entire solar system. Ganymede orbits Jupiter and is so large that it surpasses even the planet Mercury in size. Its surface is a patchwork of ancient craters, frozen ridges, and enormous icy plains. But what makes Ganymede extraordinary is something hidden deep inside. Unlike most moons, Ganymede possesses its own magnetic field. This means that deep beneath its icy crust, its interior is active enough to generate a protective magnetic environment, something normally associated with planets rather than moons. Even among the many moons of our solar system, Ganymede stands out as a world of surprising complexity. These examples reveal something important. Moons are not merely small pieces of rock orbiting planets. They can be entire worlds in their own right. Some contain oceans. Some have atmospheres. Some may even possess environments where life could exist. When astronomers realized this, the idea of moons beyond our solar system became even more exciting. Because if planets orbit distant stars, and if moons commonly form around planets, then the galaxy might contain vast numbers of moons. Worlds we have never seen, orbiting planets that circle stars thousands of light years away. In fact, some planetary systems in our galaxy may contain even more moons than our own solar system. Around giant planets, especially those similar to Jupiter or Saturn, gravitational forces can gather large disks of gas and dust. Within these disks, smaller objects can slowly form. Just as planets form around stars, moons may form around planets. Over time, these newborn moons settle into stable orbits, quietly circling their host planets for billions of years. It is a process that appears to happen naturally wherever planets form, and if this process is universal, then moons may be scattered throughout the galaxy. Billions of them, perhaps even trillions. Yet despite how common moons appear to be in our solar system, detecting them around distant planets is far more difficult. Moons are small, their signals are faint, and from our vantage point across vast interstellar distances, even large moons become extremely difficult to observe. Astronomers searching for exomoons must look for subtle clues, tiny disturbances in the motion of planets or delicate variations in the light of distant stars. The challenge is enormous, but the potential reward is extraordinary, because the discovery of even a single exomoon would confirm something remarkable, that the quiet companions we see around the planets of our own solar system may exist everywhere. Moons drifting silently around distant worlds beneath unfamiliar stars. And so, inspired by the moons close to home, our moon, Europa, Titan, Ganymede, and many others, astronomers continue their patient search. Because somewhere in the vast darkness between the stars, countless unseen moons may already be circling distant planets. Silent, hidden, waiting to be discovered. In the next part of our journey tonight, we will take a closer look at the idea itself. What exactly is an exomoon? And how might these distant moons form around planets orbiting faraway stars? Now that we have wandered among the moons of our own solar system, it becomes easier to imagine a similar idea unfolding far beyond our Sunday. Because the universe is vast, and the processes that shape planetary systems here may also shape systems around other stars. When astronomers speak about exomoons, they are referring to moons that orbit planets outside our solar system. The word itself is simple. Exo means outside. So an exoplanet is a planet beyond our solar system, and an exomoon is a moon that circles one of those distant planets. It is a quiet extension of something very familiar. Just as our moon orbits Earth, an exomoon would orbit a planet that circles another star somewhere in the galaxy. To picture this, imagine traveling to a distant planetary system many light years away. Perhaps the central star glows a soft orange, slightly cooler than our Sunday. Several planets orbit it in slow, graceful paths. One of those planets might be a giant gas world similar to Jupiter. Floating around that planet could be a collection of moons, some small, some large, some perhaps covered in ice, rock, or oceans. From the surface of such a moon, the sky might look extraordinary. The giant planet it orbits would dominate the heavens, appearing enormous and colourful overhead. And beyond that planet, the distant star would shine like a small but steady sun. This is the quiet world astronomers imagine when they think about exomoons. One of the fascinating things about moons is that they can vary tremendously in size. Some moons are little more than irregular rocks drifting through space. Mars's moons, Phobos and Deimos, are good examples. They are small, oddly shaped objects that resemble captured asteroids more than traditional moons. But other moons, can be enormous. Ganymede, the largest moon of Jupiter, is so big that it is larger than the planet Mercury. Titan, Saturn's largest moon, also approaches planetary size. These giant moons show that moons are capable of becoming full worlds in their own right. And if such large moons exist in our solar system, it is entirely possible that even larger moons could exist around distant planets. Some scientists believe that certain exomoons might be as large as Mars, or even approaching the size of Earth. Worlds large enough to have atmospheres, weather, and perhaps even oceans. But how do moons form in the first place? Understanding that question helps explain why astronomers expect exomoons to exist. There are several ways that moons can form. One common method is through co-formation. This happens when a planet is forming within a disk of gas and dust around a young star. As the planet gathers material and grows larger, a smaller disk of gas and debris can form around the planet itself. Inside that smaller disk, moonlets begin to accumulate tiny objects that gradually merge together to form larger moons. This process is very similar to the way planets form around stars. In fact, you could think of it as a miniature version of planetary formation happening around a planet instead of a star. Jupiter's large moons, Io, Europa, Ganymede, and Callisto likely formed this way. They were born from a disk of material swirling around Jupiter when the solar system was young. If giant planets form around other stars in the same way, then similar disks may form around those planets as well. And within those disks, moons may begin to grow. Another way moons can form is through capture. In this case, a planet's gravity pulls a wandering object such as an asteroid or small planetary body into orbit. Once captured, that object becomes a moon. Some scientists believe that Neptune's moon Triton may have formed this way. Triton is unusual because it orbits Neptune in the opposite direction of the planet's rotation. This backward motion suggests that Triton may once have been a separate object that was later captured by Neptune's gravity. In distant planetary systems, similar captures may happen as well. Objects drifting through space may occasionally be pulled into orbit around planets. Over time, these captured bodies become moons. A third possibility is the formation of moons through giant impacts. Our own moon likely formed in this way. Billions of years ago, a young Earth may have collided with another large object roughly the size of Mars. The collision sent enormous amounts of debris into orbit around our planet. Over time, that debris gradually gathered together to form the moon. This kind of dramatic event could also happen in distant planetary systems. When young planets collide, fragments of rock and molten material may spread into orbit. Eventually, these fragments could merge and become moons. Because these formation processes appear to be common in planetary systems, astronomers believe that moons may be extremely abundant throughout the galaxy. Every giant planet might host several moons. Some planetary systems could contain dozens. If the Milky Way contains hundreds of billions of planets, then the number of moons may be even greater. Perhaps trillions of them, each quietly circling its host planet beneath the light of a distant star. Some exomoons may resemble the icy moons of our solar system. Others could be rocky worlds with rugged landscapes and mountains. Some may orbit gas giants so closely that powerful gravitational forces heat their interiors. This process, called tidal heating, can warm the interior of a moon even when it is far from its star. Europa and Io both experience tidal heating due to Jupiter's gravity. In distant planetary systems, similar effects could occur. A moon orbiting a giant planet might contain underground oceans warmed by gravitational energy. In certain conditions, such moons might even possess environments where life could potentially exist. Yet despite all these possibilities, exomoons remain extremely difficult to observe. From our perspective here on Earth, distant planets are already faint and small. Their moons are even smaller. Detecting them requires extraordinary precision. Astronomers must watch distant stars carefully and measure tiny changes in light as planets pass in front of them. If a moon is present, it might produce a slight additional signal, a delicate ripple in the data that hints at something orbiting the planet. These signals are incredibly subtle, sometimes so subtle that they are easily hidden by noise or natural variations in the star's light. And yet, astronomers continue searching, because the discovery of even one confirmed exomoon would be remarkable. It would tell us that the processes shaping our own solar system are not unique. They occur elsewhere as well. Planets forming around distant stars, moons forming around those planets, entire miniature systems unfolding quietly across the galaxy. Perhaps somewhere, far from our sun, there is a moon with mountains and oceans. A moon where giant planets rise in the sky each night. A moon where alien tides move slowly across hidden seas. Worlds we have not yet seen, but which may already exist in the vast darkness of the universe. In the next part of our journey tonight, we will explore why these distant moons are so difficult to find. Because although exomoons may be common throughout the galaxy, detecting them from across the enormous distances of space is one of the greatest challenges astronomers face. Now that we understand what exomoons are, a quiet question naturally follows. If moons are so common in our own solar system, and if planets around other stars are now known to be abundant, then why haven't astronomers already discovered large numbers of exomoons? Why are these distant moons still hidden from us? The answer lies in something both simple and profound. The universe is unimaginably vast, and the objects astronomers are trying to observe are incredibly small. To appreciate the difficulty, it helps to imagine the scale involved. Our own moon is about 3,400 kilometers in diameter. That may sound enormous by human standards, but on the scale of astronomy, it is relatively small. Even our sun, more than 100 times wider than Earth, appears as only a bright point of light when viewed from distant stars. Now consider the challenge of detecting a moon orbiting a planet around another star located hundreds or even thousands of light years away. From that distance, both the planet and its moon are far too small to see directly. Even the largest telescopes cannot resolve them as separate objects. Instead, astronomers must rely on indirect clues. They look for subtle patterns hidden in starlight, tiny hints that reveal the presence of unseen worlds. One of the most successful methods used to discover exoplanets is called the transit method. This technique involves watching a distant star carefully and waiting for a planet to pass in front of it. When the planet crosses the star's face, it blocks a small fraction of the star's light. From Earth, astronomers see the star dim very slightly for a short period of time. If this dimming happens repeatedly, it suggests that a planet is orbiting the star. This method has been incredibly effective. Using it, astronomers have discovered thousands of exoplanets. But detecting a moon using the same method is much harder, because a moon is smaller than a planet, much smaller, and the amount of light it blocks from the star is correspondingly tiny. Imagine a planet passing in front of a star. The planet may block perhaps 1% of the star's light. That small dip in brightness can be measured by modern telescopes. But a moon orbiting that planet might block only 1/100th of that amount. The resulting signal is extremely faint. So faint that it can easily be hidden by natural variations in the star's brightness. Stars are not perfectly steady lights. They flicker slightly. They produce small flares. Their surfaces contain turbulent regions of hot plasma. All of these natural behaviors can create noise in the data astronomers collect. Within that noisy signal, the presence of a moon can be extremely difficult to detect. Another challenge arises from the motion of the moon itself. Unlike planets, which orbit stars in predictable paths, moons move around their planets as well. This means the moon's position changes constantly relative to the planet. Sometimes the moon may pass in front of the star just before the planet, sometimes just after, sometimes not at all during the transit. This shifting motion creates complex patterns in the data. Astronomers must carefully analyze many observations before they can determine whether a moon might be responsible for the signal they see. Even then, uncertainty often remains. The data can be difficult to interpret. There is also another subtle effect astronomers look for when searching for exomoons. When a planet has a large moon, the moon's gravity can cause the planet itself to wobble slightly as it orbits the star. This wobble changes the timing of the planet's transits across the star. Sometimes the transit occurs a little earlier than expected, sometimes a little later. These tiny variations are called transit timing variations. If a consistent pattern appears, it may suggest that a moon is tugging gently on the planet. But detecting these changes requires extremely precise measurements. The timing shifts may be only a few seconds, sometimes even less, and they must be measured across observations separated by months or years. Even with powerful space telescopes, gathering this level of precision is challenging. Telescopes like Kepler and TESS have provided astronomers with enormous amounts of data about distant stars and planets. But finding exomoons within that data is like searching for delicate ripples hidden within a vast ocean of light. Scientists must analyze the brightness of stars across thousands of observations. They use sophisticated computer models to simulate possible planetary systems. They compare those models with the data to see whether a moon might explain the patterns they observe. It is careful, patient work, sometimes taking years to confirm or reject a single possible detection. And then there is the final difficulty. Even when astronomers believe they have found a signal that might come from an exomoon, proving it can be incredibly difficult. Other effects can produce similar signals. Star spots on the surface of a star can create temporary dimming. Instrument noise in telescopes can introduce tiny irregularities in the data. Even additional planets in the same system can create patterns that mimic the presence of a moon. Because of these possibilities, astronomers must be cautious. They require strong evidence before declaring the discovery of an exomoon. So far, several promising candidates have been identified, but none have yet been confirmed beyond doubt. And yet, despite these challenges, astronomers remain confident that exomoons exist. The processes that create moons appear to be natural outcomes of planetary formation. Where planets form, moons often follow. Our own solar system is a perfect example. There is no reason to believe that the rest of the galaxy behaves differently. The moons are likely out there already, quietly orbiting distant planets beneath unfamiliar stars, hidden only by distance and by the limits of our current technology. But technology continues to improve. New telescopes are being built, more sensitive instruments are being developed, and astronomers are learning better ways to analyze the delicate signals hidden within starlight. With each new observation, the search becomes a little more precise, a little more hopeful, because somewhere in the vast darkness of space, a distant moon may already be revealing itself one tiny signal at a time. In the next part of our journey tonight, we'll explore the methods scientists use to search for these hidden worlds. Because even though exomoons are incredibly difficult to detect, astronomers have developed several clever techniques that may eventually allow us to discover them. Even though exomoons are incredibly difficult to detect, astronomers have not given up searching for them. Instead, they have developed clever ways to look for signs that moons might exist, even when those moons cannot be seen directly. Because when we observe distant stars, we are not really seeing the planets and moons themselves. We are watching how those unseen worlds influence the light of their stars. Tiny patterns hidden in starlight can reveal the presence of entire planetary systems, and sometimes, perhaps even moons. One of the most important techniques used in this search involves something called transit timing variations. To understand this idea, imagine a distant planet orbiting its star. Each time the planet passes in front of the star, it blocks a small fraction of the star's light. From Earth, astronomers see a tiny dip in brightness. This dip repeats every time the planet completes one orbit. Because planetary orbits are usually stable, these transits tend to occur at regular intervals. The timing is almost like the ticking of a cosmic clock. A planet might cross its star every 10 days, or every 30 days, or every year. The pattern repeats again and again. But if the planet has a large moon orbiting it, something interesting happens. The planet does not travel in a perfectly smooth path. Instead, the gravity of the moon pulls gently on the planet as they move together through space. This causes the planet to wobble slightly. And because of that wobble, the moment when the planet passes in front of the star may shift just a little. Sometimes the transit occurs a bit earlier, sometimes a bit later. These small shifts in timing are known as transit timing variations, or TTVs. When astronomers observe repeated transits and notice that the timing changes in a consistent way, it can suggest that something is tugging on the planet. That something might be a moon. Another related technique is known as transit duration variations, often called TDVs. This method focuses not on when the transit happens, but on how long it lasts. Normally, when a planet passes in front of a star, the length of time it takes to cross the star remains almost the same each orbit. But if a moon is present, the gravitational interaction between the planet and the moon can slightly alter the planet's speed or position during the transit. As a result, the transit might last a little longer one time and a little shorter the next. These tiny differences in duration are extremely subtle, but when measured carefully across many observations, they can provide another clue that a moon may be present. Detecting these variations requires instruments of extraordinary precision. Even the smallest shifts in timing must be measured with incredible accuracy. This is where space telescopes become essential. Observing from Earth is difficult because our atmosphere distorts incoming starlight. Air currents, temperature changes, and atmospheric turbulence can all interfere with delicate measurements. Space telescopes avoid this problem by operating far above Earth's atmosphere. Floating quietly in space, they can observe distant stars with remarkable stability. One of the most important telescopes for discovering exoplanets and potentially exomoons was NASA's Kepler Space Telescope. Kepler spent nearly a decade staring at a small patch of sky, carefully measuring the brightness of more than 100,000 stars. Its mission was simple but ambitious. Watch for tiny dips in starlight caused by planets passing in front of their stars. Over time, Kepler discovered thousands of exoplanets. Among its vast collection of data, astronomers began searching for even more subtle patterns. Small variations in transit timing, tiny changes in transit duration, possible hints that moons might be orbiting some of those distant planets. Although no exomoon has yet been confirmed beyond doubt, Kepler's data has revealed several intriguing candidates. Possible moons whose signals appear faintly in the measurements. Objects that scientists continue studying today. More recently, new space telescopes have joined the search. NASA's TESS telescope, for example, scans large portions of the sky looking for planets around nearby stars. Meanwhile, powerful observatories such as the James Webb Space Telescope provide astronomers with even more detailed observations of distant planetary systems. These instruments allow scientists to measure the light of stars with astonishing precision, sometimes detecting changes as small as a few parts per million. With this level of sensitivity, astronomers can continue refining their search for exomoons, looking for the delicate fingerprints that moons leave in starlight. But even with these powerful tools, the search remains challenging. Most exomoons, if they exist, are likely smaller than the planets they orbit. Their signals are faint, their gravitational effects subtle. Astronomers must analyze enormous amounts of data to separate genuine signals from random noise. Sometimes it takes years of careful study to confirm that a particular pattern is real, and even then, uncertainty can remain. Science moves slowly when dealing with objects so distant and so faint. But patience is part of the process. The search for exomoons is also a story of creativity. Astronomers continually develop new methods for interpreting the light from distant stars. They build computer models that simulate how moons might influence the motion of planets. They compare those models with real observations, looking for matches that could reveal the presence of hidden worlds. Every improvement in technology brings us closer to the moment when the first confirmed exomoon may finally be discovered. And when that moment comes, it will open an entirely new window onto the universe. Because if moons orbit distant planets, they may form miniature worlds with their own landscapes, atmospheres, and perhaps even oceans. Worlds that circle giant planets beneath alien skies. Worlds where the view of the cosmos might be very different from the one we see on Earth. In the next part of our journey tonight, we will look at the first possible hints that astronomers may already have detected such worlds. Because among the thousands of exoplanets discovered so far, a few intriguing signals suggest that distant moons may already be quietly orbiting their planets, waiting for us to confirm their existence. After years of searching and developing new methods to detect distant moons, astronomers eventually began to notice something intriguing within the enormous datasets collected by space telescopes. Tiny signals, subtle irregularities, patterns in the light of distant stars that seemed slightly different from what planets alone could explain. These were not clear discoveries yet, but they were hints. Hints that perhaps, somewhere among the thousands of known exoplanets, there might already be moons quietly orbiting their planets. The first possible exomoon candidates had begun to appear. Most of these early hints came from data collected by NASA's Kepler Space Telescope. Kepler was designed to detect planets by measuring tiny dips in starlight when planets passed in front of their host stars. But the telescope was so sensitive that it recorded enormous amounts of detailed brightness data for thousands of stars. Hidden within those measurements were incredibly subtle patterns. Some researchers wondered whether those patterns might reveal something even smaller than planets. Moons. Detecting them would be far more difficult. But Kepler's precise observations made it at least possible to try. Among the many planetary systems discovered by Kepler, one in particular began to attract attention. A distant planet known as Kepler 1625b. This planet is enormous, several times larger than Jupiter. It orbits a star located about 8,000 light-years away from Earth. From our perspective, that star appears only as a faint point of light in the constellation Cygnus. Yet the data collected from this system revealed something unusual. Each time Kepler 1625b passed in front of its star, the timing of the transit appeared slightly irregular. The planet did not cross the star at exactly the same moment every orbit. Instead, the transit times shifted just a little. Sometimes earlier, sometimes later. These variations suggested that something might be tugging gently on the planet. Astronomers began studying the data carefully. They considered many possible explanations. Perhaps another unseen planet was influencing the orbit. Perhaps the star itself was behaving in a way that altered the measurements. But another possibility began to emerge. What if the planet had a moon? A large moon, large enough to influence the planet's motion in a measurable way. In 2018, a team of astronomers led by David Kipping at Columbia University published a study describing what might be the first serious candidate for an exomoon. They proposed that the unusual signals observed in the Kepler 1625 system might be caused by a moon orbiting the giant planet Kepler 1625b. This proposed moon was given the designation Kepler 1625bi, and if the interpretation was correct, the the moon would be extraordinary. Instead of being small like most moons in our solar system, this object appeared to be enormous, possibly comparable in size to the planet Neptune. In other words, it would be a giant moon, far larger than any moon known in our own solar system. If Kepler 1625b truly exists, it would challenge many assumptions about how moons form. In our solar system, moons are typically much smaller than the planets they orbit, but this candidate moon appeared unusually large relative to its planet. Some astronomers suggested that such a moon might have formed in a different way. Perhaps it was once a planet itself that became gravitationally captured by the giant planet. Or perhaps it formed within an unusually massive disk of material surrounding the planet during its early history. Either possibility would make the system remarkably unusual. To investigate the signal further, astronomers turned to another powerful observatory, the Hubble Space Telescope. Hubble observed the Kepler 1625 system during one of the planet's transits across its star. These observations provided even more detailed measurements of the star's brightness. And once again, something interesting appeared. The transit seemed slightly distorted. The shape of the dip in brightness did not match what astronomers expected from a planet alone. Instead, the data suggested that another object, possibly a moon, might be passing in front of the star shortly before or after the planet itself. The evidence was intriguing, but it was not definitive. And this is where the story becomes more complicated. Because in science, extraordinary claims require extraordinary evidence. Many astronomers remain cautious about the proposed exomoon around Kepler 1625b. The signals observed so far are subtle. The data is limited, and alternative explanations may still exist. Some scientists argue that the irregular patterns could result from instrumental noise or other astrophysical effects unrelated to a moon. Others believe that additional observations are needed before any firm conclusion can be reached. This debate is a normal and healthy part of the scientific process. Discoveries are tested carefully. Evidence is examined from multiple perspectives. Only after repeated confirmation does a new discovery become widely accepted. For now, Kepler 1625b remains a candidate exomoon, an intriguing possibility, a hint of what might exist beyond our solar system, but not yet a confirmed discovery. Yet even the possibility of such a moon has energized astronomers around the world, because if this candidate is real, it suggests something remarkable. Large moons may exist around distant planets, perhaps even many of them, hidden among the thousands of planetary systems scattered throughout the galaxy. And somewhere among those distant systems, there may be moons with landscapes, oceans, and skies of their own. Moons where giant planets loom overhead. Moons where distant stars shine softly through alien atmospheres. Worlds waiting quietly for us to discover them. In the next part of our journey tonight, we will explore another fascinating possibility. Because some scientists believe that certain exomoons might be even larger than those in our solar system. Massive moons, orbiting giant planets, worlds that could rival planets themselves in size and complexity. As astronomers began imagining the moons that might exist beyond our solar system, they quickly realized something fascinating. The moons we know in our own solar system may not represent the full range of possibilities. In fact, some scientists believe that exomoons around distant planets could be far larger than any moon we have ever observed close to home. These hypothetical worlds are sometimes called giant exomoons or supermoons. Moons so large that they might resemble small planets in their own right. To understand why such large moons might exist, it helps to look at the environments where moons are most likely to form. In our solar system, the largest collections of moons orbit the gas giant planets. Jupiter alone hosts dozens. Saturn, Uranus, and Neptune also possess extensive families of moons. These giant planets formed early in the history of the solar system when vast clouds of gas and dust surrounded the young Sunday. As these massive planets grew, they were surrounded by swirling disks of material miniature versions of the disk that formed the planets themselves. Within these disks, smaller objects began to accumulate. Tiny particles gathered together, forming larger bodies. Eventually, these bodies became moons. This process is known as circumplanetary disk formation, and it appears to be a natural part of how giant planets evolve. The size of the moons that form in these disks depends on several factors. One of the most important is the mass of the planet itself. A more massive planet can hold a larger disk of material around it, and within a larger disk, more material is available for building moons. This means that extremely massive planets, especially those larger than Jupiter, could potentially form very large moons. Moons far bigger than those in our solar system. In some theoretical models, these moons could reach sizes comparable to Mars. That would make them far larger than any moon orbiting Earth, Jupiter or Saturn today. Such worlds would be enormous compared to most moons we know. To put this into perspective, consider the largest moons in our own solar system. Ganymede, Jupiter's largest moon, has a diameter of about 5,200 kilometers. That is already larger than the planet Mercury. Titan, Saturn's largest moon, is only slightly smaller. Both are massive worlds with complex geology and internal structures. Yet even these impressive moons are still much smaller than Mars. Mars has a diameter of about 6,800 kilometers. If moons of that size formed around distant gas giants, they would truly be extraordinary. Entire worlds orbiting other worlds. These giant exomoons might also possess fascinating environments. Because of their size, they could potentially hold thick atmospheres. Gravity on such moons would be strong enough to retain gases over long periods of time. With an atmosphere present, weather systems could develop. Clouds might drift across alien skies. Winds might shape the landscape. And if the temperature conditions were suitable, liquid water might even exist on the surface. In such cases, a giant exomoon could resemble a small planet. But with one remarkable difference. Instead of orbiting a star directly, it would orbit a planet. Imagine standing on the surface of such a moon. Above you, the sky might glow softly under the light of a distant star. But dominating the heavens would be the planet you orbit, a massive gas giant filling a huge portion of the sky. Bands of swirling clouds might stretch across its atmosphere. Storms larger than entire continents might rotate slowly across its surface. From your perspective, the planet would not simply appear as a distant object. It would loom overhead, enormous and magnificent, a constant presence in the sky. And this giant planet would also influence the moon in powerful ways. Its gravity would create strong tidal forces within the moon's interior. As the moon orbits, these gravitational forces would gently flex and stretch the moon's crust. This process, known as tidal heating, can generate significant internal warmth. We already see this effect in our own solar system. Jupiter's moon Io is the most volcanically active world known. Its interior is heated by the intense tidal forces created by Jupiter's gravity. Similarly, Europa's hidden ocean may remain liquid partly because of tidal heating. On a large exomoon orbiting a giant planet, these forces could create complex geological activity. Volcanoes, subsurface oceans, perhaps even environments capable of supporting life. Astronomers suspect that gas giant planets may be particularly rich hosts for moons, because giant planets often form in large numbers across the galaxy. Many of the exoplanets discovered so far are gas giants orbiting distant stars. Some are even larger than Jupiter. These enormous planets could potentially support systems of moons far larger and more diverse than the ones we see in our solar system. In some cases, Entire miniature moon systems may exist, several moons orbiting a single planet, each with its own landscape, climate, and geological activity. Yet despite these exciting possibilities, detecting such moons remains extremely difficult. Even if a moon were as large as Mars, it would still appear tiny when viewed from thousands of light years away. Its gravitational influence might produce small signals in the motion of its host planet. Its transit across a star might produce a faint additional dip in brightness. But separating those signals from noise requires extremely precise observations. For now, giant exomoons remain mostly theoretical, but the laws of physics do not prevent their existence. And the vast diversity of planetary systems discovered in recent years suggests that the universe may produce worlds far stranger than anything we have yet observed. Somewhere out there, orbiting a distant gas giant beneath the glow of an alien sun, a giant moon may already exist. A world as large as Mars. A world with mountains, valleys, and perhaps oceans. A world where the sky is dominated by the immense presence of its parent planet. A quiet world waiting in the darkness. In the next part of our journey tonight, we will explore one of the most fascinating possibilities of all. Because some scientists believe that certain exomoons, especially large ones, might even provide environments where life could potentially arise. Hidden oceans, warm interiors, and distant moons that may quietly harbour the ingredients needed for living worlds. When astronomers imagine the moons that might exist around distant planets, one of the most intriguing possibilities is that some of them might be more than just cold, silent rocks drifting through space. Some exomoons might be habitable. In other words, they might possess environments where the conditions could allow life to exist. This idea may sound surprising at first. After all, when we think about habitable worlds, we usually imagine planets orbiting stars at just the right distance, places where temperatures allow liquid water to remain stable on the surface. But moons introduce a fascinating twist to this picture, because a moon does not need to orbit a star directly to receive energy. It can receive energy from its host planet as well, and sometimes that energy can come from gravity itself. One of the most important processes that might make exomoons habitable is something called tidal heating. This process occurs when a moon orbits very close to a massive planet. The planet's gravity pulls strongly on the moon. As the moon travels through its orbit, the strength and direction of that gravitational pull change slightly. This constant tugging causes the moon's interior to flex and stretch, very slowly, but continuously. Over time, that gentle stretching produces heat deep inside the moon. This internal heating can warm the moon's interior even if the moon is located far from its star. In some cases, it may be enough to melt ice beneath the surface and create hidden oceans. A beautiful example of this process exists right here in our own solar system. Jupiter's moon, Europa. From space, Europa appears as a smooth, icy sphere crossed by delicate reddish cracks. These cracks mark fractures in the frozen crust. But beneath that crust, scientists believe something extraordinary may exist. A vast ocean of liquid water, hidden beneath kilometers of ice. Europa orbits Jupiter in a slightly elliptical path. As it moves closer and farther from the giant planet during each orbit, Jupiter's immense gravity gently flexes the moon. That flexing produces tidal heating inside Europa, enough heat to keep its underground ocean liquid. Despite being far from the Sunday, another fascinating moon in our solar system is Titan, the largest moon of Saturn. Titan is wrapped in a thick atmosphere composed mostly of nitrogen. In many ways, Titan resembles a frozen version of Earth. It has clouds, weather systems, rivers, and lakes. But instead of water, Titan's lakes are filled with liquid methane and ethane. These strange hydrocarbons remain liquid in the extremely cold temperatures far from the Sunday. Titan's thick atmosphere protects its surface and allows complex chemistry to occur. Some scientists believe that Titan's environment may resemble the conditions that existed on Earth billions of years ago before life first appeared. Europa and Titan show us that moons can possess remarkable environments, and these examples exist within our own solar system, so it is natural to wonder what kinds of moons might exist around planets in other star systems. In the vast galaxy, there may be moons larger than Europa, moons with thicker atmospheres than Titan, moons warmed by both starlight and tidal heating from giant planets. Some of these worlds might orbit within the habitable zone of their stars, the region where temperatures allow liquid water to exist. In such situations, a moon might receive warmth from multiple sources, from its star, from the gravitational flexing caused by its planet, and sometimes even from reflected light from the planet itself. Imagine standing on such a moon. Above you, the sky glows softly beneath a distant sun, but dominating the heavens would be the enormous planet you orbit, a vast gas giant filling much of the sky, its swirling clouds stretching across the horizon like a living painting. As the moon travels through its orbit, tides may slowly rise and fall in the moon's oceans. Warm currents might circulate beneath the surface. Volcanic activity could release gases into the atmosphere. All of these processes could create environments where chemistry becomes increasingly complex. In such conditions, scientists sometimes wonder whether life might emerge. Of course, the presence of liquid water alone does not guarantee that life exists. Life requires many ingredients: stable environments, complex chemistry, time. Yet the more we learn about moons in our own solar system, the more we realize that habitable environments may exist in unexpected places. Even small moons can contain hidden oceans. Even distant worlds can possess active geology. And in the vast diversity of planetary systems scattered across the galaxy, there may be many different kinds of moons. Some icy, some rocky, some with atmospheres, some warmed by tidal forces, each one representing a possible environment where life might one day be found. Astronomers searching for exomoons are especially interested in these possibilities because moons offer something unique. A moon can orbit a giant planet located within the habitable zone of a star, but the moon itself may have conditions different from the planet it orbits. It may be smaller, cooler, possibly more stable. In some scenarios, a moon might even be more hospitable to life than the planet itself. For now, these ideas remain possibilities. We have not yet confirmed the existence of a habitable exomoon, but the clues from our own solar system suggest that such worlds may not be rare. Somewhere in the Milky Way, a distant moon may already possess oceans beneath its surface, or clouds drifting across alien skies, quiet environments where chemistry unfolds slowly beneath the light of a distant star. In the next part of our journey tonight, we will explore another fascinating aspect of moons beyond our solar system. Because if exomoons exist in great numbers, they may display incredible diversity, strange and exotic worlds with landscapes far different from anything we know here on Earth. As astronomers continue imagining the moons that may exist beyond our solar system, one thing becomes increasingly clear. If exomoons are real, and most scientists believe they are, then the diversity of these worlds may be extraordinary. Even within our own solar system, moons already display remarkable variety. Some are frozen worlds covered in ice. Some are volcanic landscapes shaped by fire. Some possess thick atmospheres and strange weather. If such diversity exists close to home, then across the vast number of planetary systems in our galaxy, moons may come in forms we have never even imagined. Quiet worlds of ice, stormy moons wrapped in thick clouds, volcanic landscapes glowing with lava, entire oceans hidden beneath frozen crusts, each type revealing a different possibility for how moons can exist. One of the most dramatic kinds of moon that might exist is the lava moon. We already know a powerful example in our own solar system, Io, one of Jupiter's 4 largest moons. Io is the most volcanically active world known. Its surface is constantly reshaped by eruptions that spew molten rock high above the landscape. Gigantic volcanic plumes rise hundreds of kilometers into space. Bright rivers of lava spread across the surface. The reason for Io's intense activity is the powerful gravitational pull of Jupiter. As Io orbits the giant planet, Jupiter's gravity stretches and squeezes the moon's interior. This constant flexing generates enormous heat deep within the moon. The result is a world of relentless volcanism. If similar tidal forces exist in distant planetary systems, exomoons could also experience extreme heating. Some might be covered in glowing lava fields. Others might possess vast volcanic regions that continuously reshape the landscape. From space, such moons might appear as glowing orange worlds orbiting giant planets. At the opposite extreme are icy moons. Many moons in our solar system are dominated by ice rather than rock. Europa, Enceladus, and several moons of Uranus and Neptune fall into this category. These moons often appear bright and reflective, their surfaces covered in frozen water or other exotic ices. But beneath that frozen exterior, surprising things can occur. In some cases, thick layers of ice hide subsurface oceans, liquid water trapped beneath the crust, protected from the cold vacuum of space above. Europa is perhaps the most famous example. Beneath its icy shell may lie a deep global ocean, one that contains more water than all the oceans on Earth combined. If tidal heating provides enough energy, these oceans may remain liquid for billions of years. And in the darkness beneath the ice, complex chemical environments could develop. Similar icy moons might exist in other planetary systems. Moons where oceans remain hidden beneath frozen surfaces. Worlds of ice that quietly contain liquid seas beneath their crusts. Another fascinating possibility is the existence of ocean moons. These are moons where water may exist directly on the surface rather than beneath ice. If a large moon formed within the habitable zone of its star, temperatures might allow surface oceans to remain stable. In that case, the moon might resemble a small ocean planet. Vast seas stretching across the landscape, clouds forming above warm waters, rain falling across alien coastlines. Such moons might also experience tidal forces from their host planets. These tides could cause oceans to rise and fall across the surface. Waves might move slowly across enormous planetary seas. And if the moon possesses an atmosphere, weather systems might circulate across the globe. These worlds would be among the most fascinating places in the galaxy. Moons where oceans reflect the light of distant stars and giant planets loom overhead in the sky. Some moons might also possess thick atmospheres. Titan, Saturn's largest moon, is an excellent example. Titan's atmosphere is denser than Earth's and filled with complex organic molecules. The thick haze surrounding the moon gives its sky a golden color. Sunlight filters through the atmosphere, creating a dim but mysterious environment at the surface. Rivers and lakes of liquid methane carve channels through Titan's landscape. Clouds drift slowly across the sky, and seasonal cycles influence the moon's weather. If moons like Titan exist around distant planets, they might display even more exotic environments. Different atmospheric compositions, strange chemistry, unfamiliar weather patterns, each moon becoming a unique world shaped by its location and its history. In some planetary systems, moons might experience combinations of these features. An icy moon with a subsurface ocean and a thin atmosphere. A volcanic moon orbiting extremely close to its giant planet. An ocean moon warmed both by its star and by tidal heating. Because the galaxy contains such enormous diversity among its planets, there is every reason to believe that moons may also display astonishing variety. The possibilities stretch far beyond the examples we know, and this diversity makes the search for exomoons especially exciting. Every moon discovered would reveal a new type of world, a new environment shaped by gravity, chemistry, and time. Some might resemble the moons of Jupiter or Saturn. Others might be unlike anything found in our solar system. Entirely new classes of celestial bodies waiting to be explored. Somewhere in the galaxy, a lava moon may glow softly as rivers of molten rock flow across its surface. Elsewhere, an icy moon may hide a dark ocean beneath its frozen crust. And around distant planets, thick clouds may drift across the skies of moons wrapped in dense atmospheres. Quiet worlds orbiting giant planets beneath unfamiliar stars. In the next part of our journey tonight, we will imagine something even more poetic. Because on distant exomoons, the skies themselves might look very different from the ones we know on Earth. Moons may rise and set in unfamiliar ways. Giant planets may dominate the heavens, and the night sky could display cosmic views unlike anything we have ever seen. When we imagine moons around distant planets, one of the most beautiful ideas is how those moons might transform the skies of the worlds they orbit. Here on Earth, we are used to seeing a single moon. It rises slowly over the horizon. It glows softly above quiet landscapes. And once each month, it becomes a full luminous disk lighting the night. But across the galaxy, the skies of other worlds may look very different. Some planets may have not just one moon, but several. Entire families of moons orbiting their planets in graceful patterns. From the surface of such a world, the sky could become a constantly changing cosmic display. Multiple moons drifting across the heavens. Some small and distant, others large enough to dominate the entire sky. In our own solar system, we already see hints of what such skies might look like. If you were standing on the surface of Jupiter's moon Europa, for example, the giant planet Jupiter would fill a vast portion of the sky. It would appear enormous, many times larger than our moon appears from Earth. Its swirling clouds and colourful bands would stretch across the heavens. And around Jupiter, other moons would move through the sky. Io, Ganymede, Callisto, each one rising and setting in slow, silent motion. From that icy landscape, the sky would feel alive with celestial movement. On distant exomoons, these effects might be even more dramatic. Imagine standing on a moon orbiting a giant planet in another star system. Above you, the planet looms like a massive world suspended in the sky. Its atmosphere glows with reflected starlight. Cloud systems swirl across its surface. Storms larger than entire continents rotate slowly across its atmosphere. And around that planet, other moons move through their own orbits. Sometimes 2 moons might rise at the same time, sometimes 3, their soft light casting overlapping shadows across the landscape. Occasionally, these moons might align in ways that produce extraordinary celestial events. Eclipses could become common. A smaller moon might drift across the face of a larger one. A moon might pass in front of the distant star, temporarily dimming the daylight. Or the giant planet itself might block the starlight for a short time, plunging the moon into a brief twilight. On Earth, solar eclipses are rare and dramatic events. But on some exomoons, eclipses might occur regularly, perhaps several times during each orbit. The sky darkening briefly as one celestial body slides across another. A silent cosmic choreography. Another fascinating effect involves tides. Here on Earth, the gravity of our moon pulls gently on our oceans. As Earth rotates, this gravitational influence creates the rising and falling of tides along our coastlines. But on moons orbiting giant planets, tidal forces could be far stronger. The massive planet would exert powerful gravitational pull on the moon. If the moon possessed oceans, those oceans might experience enormous tidal movements. Seas rising and falling dramatically as the moon moves through its orbit. In some cases, tides might lift ocean surfaces hundreds of meters higher before letting them fall again. Slow, rhythmic movements of water shaped by the gravity of a nearby giant world. These tidal forces could also influence the moon's landscape. Coastlines might shift slowly over time. Powerful currents might circulate through vast oceans. Tidal heating within the moon's interior could fuel geological activity. Volcanoes might form along tectonic boundaries. Warm hydrothermal vents could release minerals into underwater environments. Even the motion of the oceans might influence the moon's climate and weather. The interaction between gravity, water, and planetary motion would create dynamic environments unlike anything we see on Earth. The visual beauty of these alien skies might also be extraordinary. Imagine watching a sunset on such a moon. The distant star sinks below the horizon. The sky darkens slowly, and rising above the landscape is the enormous silhouette of the giant planet, its curved edge glowing faintly in reflected starlight, cloud bands shimmering across its atmosphere. Nearby moons might appear as bright points moving slowly against the stars, and sometimes the giant planet itself might reflect enough light to illuminate the landscape below. On some moons, the night might never become completely dark. Planet shine, the light reflected from the giant planet, could cast a gentle glow across the terrain. Mountains and valleys faintly visible under alien skies. These views would remind any observer that moons are not isolated worlds. They exist within complex systems. Planets, moons, and stars all interacting through gravity and motion. Every orbit shaping the environment of the worlds within it. Every alignment creating new patterns in the sky. In such systems, the heavens themselves become part of the landscape, a constantly changing display of celestial motion. Somewhere in the galaxy, a moon may already exist where 2 or 3 moons rise together in the sky, where a giant planet fills half the horizon, where eclipses occur regularly and tides shape vast oceans, worlds where the sky itself tells a story of gravity and motion, worlds we have not yet seen, but worlds that may already be circling distant planets beneath unfamiliar stars. In the final part of our journey tonight, we will look ahead to the future of astronomy, because with new telescopes and more advanced instruments, scientists hope that one day we may finally discover and study these distant moons, directly revealing the hidden companions that orbit planets across the galaxy. As we reach the final stage of our quiet journey through the world of exomoons, it becomes clear that the story of these distant moons is still only beginning. For now, exomoons remain hidden. Astronomers have discovered thousands of planets orbiting distant stars, but the moons that may circle those planets are still waiting to be revealed. Yet, the search continues, and with each new generation of telescopes, scientists move a little closer to uncovering these quiet companions of distant worlds. The discovery of exomoons depends greatly on the tools we use to observe the universe. Over the past few decades, astronomy has experienced a remarkable transformation. Telescopes have become more powerful, instruments have become more precise, and computers have become capable of analyzing enormous amounts of data collected from distant stars. One of the most important milestones in this journey has been the launch of powerful space telescopes. These observatories allow astronomers to observe the cosmos with extraordinary clarity. Floating above Earth's atmosphere, they avoid the turbulence and distortion that affect ground-based telescopes. From this stable vantage point in space, they can measure the brightness of distant stars with astonishing precision. One of the most remarkable instruments ever launched into space is the James Webb Space Telescope, often called JWST. Unlike earlier telescopes, JWST observes the universe primarily in infrared light. This allows it to detect faint heat signatures and subtle variations in starlight that were previously impossible to measure. JWST is designed to study many of the most distant and ancient objects in the universe, but it is also extremely valuable for studying exoplanets and the environments around them. As JWST observes planets passing in front of their stars, it can measure tiny changes in the light from those stars. These changes can reveal details about planetary atmospheres and, potentially, about moons. Although JWST was not specifically designed to detect exomoons, its sensitivity may help astronomers identify promising candidates. Each observation adds another piece to the puzzle. Beyond JWST, even more powerful telescopes are already being planned. Future space observatories such as the Nancy Grace Roman Space Telescope will survey large areas of the sky with incredible precision. Meanwhile, massive new ground-based telescopes are under construction. The extremely large telescope in Chile will have a mirror nearly 40 meters wide, larger than any optical telescope ever built. Such instruments will collect enormous amounts of light from distant stars. This increased sensitivity may allow astronomers to detect the faint signals produced by moons orbiting exoplanets, signals that are currently just beyond the reach of our instruments. Astronomers are also developing new techniques to interpret the data collected by these telescopes. Advanced computer models can simulate how a moon would influence the motion of a planet. Machine learning algorithms can analyze huge datasets and search for subtle patterns that human observers might overlook. With each improvement in technology, the chances of detecting exomoons increase. It is a quiet race against the limits of observation, a patient search across the enormous distances of space. And many scientists believe that the discovery of the first confirmed exomoon may not be far away. Some promising candidates have already appeared in astronomical data, signals that hint at moons orbiting distant planets. But confirming such discoveries requires careful analysis and repeated observations. Science advances slowly when dealing with objects so distant and faint. Yet history shows that discoveries often arrive sooner than expected. Just a few decades ago, astronomers were not even certain that planets existed around other stars. Today we know of thousands. It seems likely that moons will follow. When the first exomoon is finally confirmed, it will represent an important moment in astronomy, because it will show that the structures we see in our own solar system planets accompanied by families of moons are not unique. They are part of a much larger cosmic pattern. Across the Milky Way, countless planetary systems may contain moons quietly orbiting their planets. Worlds illuminated by distant stars. Worlds shaped by gravity and time. And once astronomers begin discovering these moons, the next step will be to study them in detail. Some may prove to be icy worlds with hidden oceans. Others may possess atmospheres and clouds. Some may orbit giant planets within the habitable zones of their stars. In those environments, moons could potentially become places where life might emerge. The discovery of such worlds would expand our understanding of where life might exist in the universe. Not only on planets, but also on moons. Perhaps somewhere in the galaxy, a distant moon already circles its planet beneath the light of a quiet star. Oceans rising and falling with gentle tides. Clouds drifting across alien skies. A world we have not yet seen, but which may soon reveal itself. Because as our telescopes grow more powerful and our understanding deepens, the hidden moons of the galaxy may gradually emerge from the darkness, one discovery at a time. And so the search continues, quiet, patient, looking for the faintest hints of worlds orbiting worlds across the vastness of space. Moons that may one day become familiar names in astronomy. Moons that may transform our understanding of planetary systems. Moons that may show us just how rich and diverse the universe truly is. As our gentle journey through the idea of exomoons comes to its quiet end tonight, it is comforting to pause for a moment and reflect on the vastness of the universe. In our own solar system, moons are everywhere. They circle planets silently, moving through their orbits in patient rhythms that have continued for billions of years. Some are frozen worlds of ice. Some are volcanic landscapes shaped by fire. Some may hide oceans beneath their surfaces. Each one a small but fascinating world of its own. And if such diversity exists here, around just one ordinary star, then it is natural to imagine that similar worlds may exist across the galaxy. The Milky Way alone contains hundreds of billions of stars. Around many of those stars orbit planets. And around some of those planets, there may be moons. Perhaps not just a few, but millions, maybe even billions. Quiet companions circling distant planets beneath unfamiliar suns. Worlds we have not yet seen, but worlds that may already exist. Some of those moons may resemble the icy worlds of our own solar system, hidden oceans stretching beneath frozen crusts, dark seas slowly warmed by tidal forces from giant planets. Others might be rocky landscapes where giant planets dominate the sky. And in some places, moons may orbit within systems that contain multiple companions. 2 moons rising together in the evening sky. 3 or 4 drifting slowly across the stars. Alien night skies filled with gentle celestial motion. Imagine standing on one of those distant moons. The ground beneath your feet feels unfamiliar. Perhaps icy, perhaps rocky, perhaps covered in oceans that stretch toward the horizon. Above you, the sky glows beneath the light of a distant star, but dominating the heavens is the giant planet you orbit. It hangs enormous in the sky, its clouds glowing softly with reflected starlight, and slowly rising beside it, another moon, then another. Worlds drifting silently through the darkness together, a quiet, cosmic dance unfolding above an alien landscape. Somewhere out there in the vast galaxy, scenes like this may already exist. Moons circling distant planets, oceans rising and falling with quiet tides, clouds drifting beneath unfamiliar skies, worlds that remain hidden from our view for now, but which may one day be discovered by the careful eyes of astronomers. And until that day arrives, we can simply imagine them. Distant moons, silent oceans, alien skies filled with gentle light, the quiet companions of planets scattered throughout the universe. Now, as our exploration of exomoons comes to an end, it is time to let your thoughts grow calm and still. Take a slow breath. Allow your mind to drift peacefully through the vastness of space, and imagine yourself standing on a quiet world far from Earth, watching strange and beautiful moons rise slowly into the sky. Good night, sleep well, and as the soft ambient music begins to play, let the gentle sounds carry you into a peaceful and restful sleep beneath the quiet moons of distant worlds.